Let's do some more examples finding domains of functions. So let's say I had the function g of x. So this is our function definition here. It tells us, look, if we have an input x, the output g of x is going to be equal to 1 over the square root of 6 minus, let me write this a little bit neater, 1 over the square root of 6 minus the absolute value of x. So like always, pause this video and see if you can figure out what is the domain of this function based on this function definition. What is the domain of g? What is the set of all inputs for which this function is defined? All right, so to think about all of the inputs that would allow this function to be defined, it might be easy to think, well, when does this function not get defined? Well, if we're divided by 0, then we're not going to be defined. Or if we have a negative under the radical. So if you think about it, if what we have under the radical is 0 or negative, if it's 0 or negative, if it's 0, you can take the principal root of 0, it's going to be 0, but then you're going to divide by 0, and that's going to be undefined. And if what you have under the radical is negative, then the principal root isn't defined for a negative number, or at least the classic principal root isn't defined for a negative number. So if 6 minus the absolute value of x is 0 or negative, this thing isn't going to be defined. Or another way to think about it is, it's going to be defined. So g is defined if g is defined if 6 minus, and maybe I could write if and only if. Sometimes people write if and only if with two f's right there. If g is defined if and only if, this is kind of a mathy way of saying if and only if 6 minus the absolute value of x is greater than 0. It has to be positive. If it's 0, we're going to take the square root of 0 as 0, and you're going to divide by 0. That's undefined. And if it's less than 0, then you're trying to find the principal root of a negative number. That's not defined. So let's see. G is defined if and only if this is true. And let's see, we could add the absolute value of x to both sides. We could add the absolute value of x to both sides, and then that would give us 6 is greater than the absolute value of x, or that the absolute value of x is less than 6. Or we could say that, let me write it that way, the absolute value of x is less than 6. Or another way of saying that is x would have to be less than 6 and greater than negative 6. Or x is between negative 6 and 6. These two things are equivalent. If the magnitude of x is less than 6, then x is greater than negative 6 and less than positive 6. So if we wanted to write the domain in kind of fancy domain set notation, we could write the domain of g is going to be x, all the x's that are a member of real numbers, such that negative 6 is less than x, which is less than 6. And we're done. Now let's do another one. And this one's going to get even a little bit hairier, just for kicks. All right. So let's say that I have h of x is equal to, and I'm going to have kind of a composite definition here. So let's say it's x plus 10 over x plus 10 times x minus 9 times x minus 5 times x minus 5. And it's this if h of x is this if x does not equal 5, and it's equal to pi if x is equal to 5. So once again, pause this video. Think about what is the domain of h, or another way to think about it, when is h not defined? So let's think about it. So what would make h not defined? So if x is anything other than 5, we go to this clause. If it's 5, we go to this clause. So in this clause up here, what would make this thing undefined? Well, the most obvious thing is this: if we divide by 0. So what's going to cause us to divide by 0? So if x is equal to, let me write it here. So we're going to divide by 0. Divide by 0. That would happen if x is equal to 9. That would happen if x is equal to negative 10. x is equal to negative 10. Now we have to be careful. Would that happen if this was the only definition here? It would happen when x is equal to 5. But remember, when x equals 5, we don't look at this part of the compound definition. We look at this part. So it's true that up here you would be dividing by 0 if x equaling 5, but x equaling 5, you would never even look there. If our input is 5, you use this part of the definition. So you would divide by 0, maybe I should write it this way, divide by 0 on, I guess you could say, the top clause, or the top part of definition, if x equals 9, x equals negative 10, and that's it, because x equals 5 doesn't apply to this top part. If this clause wasn't here, then yes, you would write x equals 5. Now, we're almost done, but some of you might say, wait, but look, can't I simplify this? I have x plus 10 in the numerator, x plus 10 in the denominator. Can't I just simplify this and then that'll disappear? And you could, except if you did that, you are now creating a different function definition. Because if you just simplify this and you just said 1 over x minus 9, 1 over x minus 9 times x minus 5, this is now a different function. That one actually would be defined at x equals negative 10, but the one that we have started with, this one is not. This is, you're going to end up with 0 over 0. You're going to end up with that indeterminate form. So for this function, exactly the way it's written, it's not going to be defined when x is equal to 9 or x is equal to negative 10. So once again, if we want to write it in our fancy domain set notation, the domain is going to be x, all the x's that are a member of the reals, such that x does not equal 9 and x does not equal negative 10. Any other real number x, it's going to work, including 5. If x equals 5, h of 5 is going to be equal to pi, because you default to this one over here. H of 5, you say, okay, x equals 5. We do that one right over there. Now, if you gave x equals 9, you're going to divide by 0. X equals negative 10, you're going to divide by 0. But it's going to work for anything else. So that right over there is the domain.